In this video, I'll introduce section 4.7, which is all about L'Hopital's rule. And it is a French name named after the person who determined that this rule actually works, and it's actually a helpful shortcut. And so again, his name is L'Hopital. And so what we're going to be trying to do in this section is to evaluate limits. And specifically, we're going to be evaluating limits of rational functions. And so this kind of goes back to the beginning of the calculus course, where we didn't know how to take a derivative at the time, and we were just finding limits of different functions. And so now that we know how to find derivatives of just about anything, we're going to combine finding derivatives with evaluating limits, and that's where L'Hopital's rule comes into play. So when I say rational functions, I mean fractional expressions. So if I have a function in the numerator and a function in the denominator, that creates a rational function when you put the numerator and denominator together. So we're going to be looking at finding the limit of these rational functions as x approaches some value a. And L'Hopital's rule says that if you're finding your limit and you get an indeterminate form, of infinity over infinity, or 0 over 0, then there's a special shortcut that we can use in order to find the limit of that function. So specifically, these indeterminate forms, infinity over infinity and 0 over 0, these are things that we can't actually calculate. So L'Hopital says that if that happens, then we can actually figure out the limit of the rational function by separately taking the derivative of the top and then separately taking the derivative of the bottom and then evaluating that limit using direct substitution. So direct substitution once we've taken the derivative of the top and the derivative of the bottom. And that's essentially what L'Hopital's rule is. Helps us find the limit by taking the derivative of the numerator and the denominator and then using direct substitution. So you want to be careful not to confuse this with the quotient rule. If I were just asking you to find the derivative of something that was rational, you would have to use that quotient rule. But in this case, we're not trying to find the derivative. That's not the goal. The goal is to evaluate the limit. It just so happens that the derivative helps us get there. So let's take a look at a couple of examples. And in example 1, let's try to find the limit as x approaches 2 of the function x squared minus 2x over 8 minus 6x plus x squared. So if you go back to chapter 2 in this course, we did evaluate limits that looked like this all the time. One of the strategies was that direct substitution strategy, which is exactly what we would do here. And if we use that direct substitution strategy, we will have 2 squared minus 2 times 2 on the top, and then 8 minus 6 times 2 plus 2 squared on the bottom. And if you do a couple of quick calculations, you're going to find out that the top is 0 and the bottom is 0, and you're unable to calculate that in order to say what the limit would be. So in chapter 2, we tried to factor and cancel common factors in order to help us with that direct substitution process. So L'Hopital's rule basically replaces that. You could try to factor and see if there are any common factors that cancel and see what you get. But sometimes they're not factorable, and so sometimes you run into that issue where nothing cancels, and that's where L'Hopital's rule can replace the entire process, and you can find the limit that way. So what I'm going to do is take the derivative of each part. So I'm going to take the derivative of the top, 2x minus 2, and I'm going to take the derivative of the bottom, and I'm going to write it in descending order, so that'll be 2x minus 6. And now we can use direct substitution to evaluate that limit. And if we do, we're going to plug 2 into the top, and we're going to plug 2 into the bottom, and we're going to get 2 over negative 2, which is negative 1. So it turns out that this limit should equal negative 1. So that's one example of using L'Hopital's rule in order to evaluate a limit. Let's look at another example. In this example, we'll calculate the limit as x approaches 0 of 1 minus the cosine of 3x over 8x squared. So again, we're calculating or evaluating a limit of a rational function that has a numerator and denominator, and our first step would ordinarily be to try direct substitution and see if that gets us to where we want to be. So if I plug 0 into this function, I'll have 1 minus the cosine of 0 over 0. Remember that the cosine of 0 is 1. So I get 0 over 0. Now, when you're evaluating these limits, you do have to do this as a first step. You do have to try that direct substitution in the first place to see that it gives you a L'Hopital form. Okay? And so remember that our L'Hopital forms are infinity over infinity or 0 over 0. And you do have to verify that you get that first before you go taking the derivative of the top and the bottom and using that L'Hopital's rule. Okay, so L'Hopital requires us to check to see that we have one of his indeterminate forms before we follow through with evaluating the limit. You can, of course, do that part in your head, but it does need to be done in order to verify that L'Hopital's rule applies. All right, it applies here because we got the indeterminate form of 0 over 0. So what we're going to do next is we're going to rewrite the limit by taking the derivative of the top and the derivative of the bottom separately. So in the top, the derivative of 1 will be 0. I have a negative sign. The derivative of cosine is the derivative of cosine is negative sine, is what I mean to say, but then there's also a negative sign in the front. So we end up with positive sine 3x. Chain rule says I then have to multiply by 3. Notice I put parentheses in here that weren't there before. They're optional. Let's take the derivative of the bottom. 8 times 2 is 16, x to the first. Alright, so that was L'Hopital's rule. Now let's see if direct substitution is going to get us the answer to the limit. So I'm going to plug 3 in. 3 times the sine of 3 times, I'm going to plug 0 in, is what I mean to say. Plug 0 in. So 3 times the sine of 3 times 0 is 3 times the sine of 0 over 0. Think about what the sine of 0 is, and it's still 0. So it looks like I'm getting another L'Hopital form when I try to evaluate the limit for the second time. So what you need to do is you need to repeat L'Hopital's rule until you get a constant for your limit. Okay, so you need to repeat it until you get a constant. So sometimes you have to do L'Hopital's rule a couple of times because I've got 0 over 0, I used L'Hopital's rule, and I still have 0 over 0. So let's try it again. Perfectly fine to do it several times. All you're really doing is taking derivatives of some fairly simple functions since you don't have to deal with any quotient rules. Taking the derivative of here, the derivative of sine is cosine, so it'll be 3 cosine 3x times another 3 because of the chain rule. So that's 9 cosine 3x, again those parentheses are optional, over 16. Now, once I'm able to get a variable out of the denominator, I've taken the derivative a couple of times until I just have a constant in the denominator. That's going to be a big help. That's going to be the key, the clue to letting you know that you're actually going to get a constant answer this time when you use direct substitution. So I'm going to take 9 times the cosine of 3 times 0, which is 0, and divide it by 16. The cosine of 0 is 1, so you get 9 over 16 as the limit of this function. Okay, so you have 2 examples here of using L'Hopital's rule, and each of these examples had you using the indeterminate form of 0 over 0, and so we checked it. We used L'Hopital's rule. Sometimes we have to do several iterations of L'Hopital's rule, but we know that we've got our answer when we have a constant after we've done our direct substitution. So in the first example, we had a constant answer of -1, and now we have a constant answer of 9/16 in example 2. Let's move on and look at indeterminate form infinity over infinity. All right, so next example. Let's find the limit as x approaches infinity of 3e to the 3x over 3e to the 3x plus 5. So we're finding the limit of this rational function. So first of all, let's try direct substitution. Because in order to use L'Hopital's rule, we have to make sure we're in a L'Hopital form. We don't know that we are yet. Let's plug infinity in. We have 3e to the 3 times infinity, sorry. 3 times infinity, let me write that. Even though it's technically an incorrect thing to do, we can't really substitute infinity into a function and evaluate it. It might just help you to visualize what we're working with here. So if you take infinity and multiply it by a constant of 3, it's still infinity. If you take e and raise it to an infinite power, it's still infinity. Multiply that by 3, it's still infinity. So the top is going to infinity. Okay? In the bottom, we've got that same thing, essentially. This all becomes infinity or goes to infinity. And if you add 5 to infinity, you're still at infinity. That infinity is a pretty abstract concept that's kind of hard to visualize sometimes. But when we add things to infinity or multiply infinity by constants, they're still infinity. So this is one of L'Hopital's indeterminate forms, and when we have a limit that is in that indeterminate form, we use L'Hopital's rule.